Today's topic is the demerits of the particle method and my solution for these problems. As I said, particle method is very powerful for simulating flow field around complex geometry. It can handle three-dimensional complex geometry. But they have problems in some points. One is for providing a perfectly smooth surface. It will be solved by using imaginary imaging of actual fluid particles and dummy particles. If we provide dummy particles in mirror position, it will show perfectly smooth surfaces. So also boundary condition is possible. The concept is almost the same in the mesh-based method. The remaining problem is, I guess, this one, resolution control. In incompressible flow, the density number of particles in a unit volume is constant. So the spatial resolution is same all over the computational domain. But as you saw in the mesh-based method, we have to provide higher spatial resolution around the body surface to evaluate the thin boundary layer. So the present usual particle method can be considered as the rectangular regular grid with equal spacing. This is very classic one. At present, we do not use this type of simple situation. But usual particle method is in this level. So our intention is to extend the present particle method from this level to this level. It will provide higher resolution around the body surface for accurate calculation of boundary layer treatment. So one approach is to provide variation of particle size. This will illustrate one situation. It shows standard size of particles and its smaller particles. So in this layer, it shows higher spatial resolution. And also, this shows three layered particle size changes. If we can provide this kind of situation, we can highly reduce the number of required computational resource. Please imagine if we have to calculate only using this size of particles, the required number of particles is very significant. So the required extension is to allow the merge and division of particles. if one particle will be divided into two or more particles, it will provide higher resolution. In this case, in the size of particle in this layer is half radius of the standard one. So in this case, I divided one particle into 4 small particles. And also, this particle will be divided into 4 further smaller particles. So this particle is the mass of this particle is 1/16 of this standard size. The required one for the treatment, we have to consider the possible situations. In this case, this picture shows the condition when particle J and the particle K are merged into one larger particle. It is particle L. So this direction is the merge of particles. And naturally, the other side of change from this one to this one indicates the division of particles for higher resolution. We have to consider this situation to check the consistency in the fluid dynamics. In actual fluid, there is no phenomena of such merge and division of fluid particles. So the required condition is that this change at this change of situation does not affect to particle I. If particle I does not get any influence of division or merge, the fluid simulation can be continued. The discussion requires long talks, so I can show you only the essence. First thing is we need modification of weight function, numerical particle number density. In the original MPS method, this part is the numerical number density. But the difference is now the mass of the particle, mass of each particle is not constant. So Mj indicates the mass of particle J. And we need another additional term. This is index of this mass is I. It is required because from the viewpoint of particle J, we can consider this situation that Pj, particle J, absorbs particle K. So from the viewpoint of particle J, the other particle is coming inside. For particle J have to continue the simulation without the effect of this capturing the other particle. The main problem occurs in the leveling of particle number density. Before merge, particle J have very close neighbor particles. So particle number density at this point is high. After the merge, one particle is inside the particle J itself, but we have to consider the numerical density should be constant from this situation to this situation. To solve the situation, I add this term. So in the extended model, all particles have their self-contribution to the numerical density. Since the other neighbor particle is now going to inside, so the resultant numerical number density can be constant after the before and after the merge or division of particles. Other consideration is for the gradient model. This is original gradient model I have shown you in the last class, but it has some problems because we can consider the pressure gradient is the interaction between particles. If there are two particles, pressure force is usually a repelling force. So particle I push the particle J, and also particle J push the particle I. So this is the force from J to I, and this is a force from particle I to J. To get the assurance of energy conservation, these two forces should be the total of this force should be zero. Otherwise, there will be the increase or decrease of total energy. But this feature is not automatically satisfied in the original pressure gradient model. You can divide this pressure gradient into the interaction among particles. Pressure gradient can be calculated by among the surrounding particles, and it is actually the summation of total force. These forces come to surrounding particles. So the action from particle J to particle I is one component of this summation. But Pj minus Pi indicates the it does not lead to this symmetricity. So I changed the model to this one. Actually, the result is the same if we have sufficiently enough neighboring particles. After this modification, we can consider the action like this. Since it has Pj plus Pi, it is equivalent to consider the midpoint pressure. It is Pi plus Pj divided by 2. It is average of pressure, average of average of pressure between two particles. The model is the particle gets the influence of this midpoint pressure. So automatically the effect from J to I and I to J is the same. This is the result of the modification of the gradient model. And also, similar consideration is applied to Laplacian model. In this case, there will be interaction, diffusive exchange of momentum between particles. If this particle I have high momentum and the surrounding particle have smaller moment, this excess of momentum will be distributed to other particles. So diffusion model is like this. But in the original model, the exchange of momentum from, if this is particle J, there will be an exchange of momentum from I to J. However, the Laplacian calculation, it is the diffusion term calculation, will be done separately for particle I and particle J. So in original model, there is no assurance of the conservation of momentum. In the discuss of finite volume method, we consider the flux between the two control volumes. It is for the assurance of conservation. The amount, in this case, control volumes are I and I plus 1. The amount of control volume I gives to I plus 1 should be equal to the flux I plus 1 receives from the ith control volume. To satisfy the same condition, we changed the formation slightly. And also in the consideration, the flux is proportional to the mass of each particles. So after this modification, Now we can consider the asymmetric exchange of momentum between large particles and small particles. Although the situation occurs in the present simulation, the moment, the flux of momentum, it goes to particle I to j is equal to the amount equal to the amount that particle j receives from the particle I. This is before considering the control of resolution. This is a very simple case. It is low resolution case. This is the wedged shape is going into the water surface. This is a result of resolution control. If you will see closely, you can see the division of particles. This part is in standard size, and the particles inside the specified distance from the body boundary will be divided into 4 particles in this case. In two-dimensional case, one particle will be divided into 4 particles. So that each mass of a smaller particle is a quarter of the original mass. So you can see the detail around the body surface is improved in this consideration. So this is some comparison between experimental work and numerical result. Unfortunately, I cannot find good experimental result in the updated one. This one is very old one. It shows the experiment in two-dimensional tank. The body is going into water surface. Although it is not appear in the picture, the very huge mass is connected to this one to keep the falling speed after the impact. These are air bubbles to visualize the motion of fluid. So it is very old, but it contains many techniques and idea of researchers in the day. This is original uniform flow simulation. The agreement between these two results is not well in the original resolution, but it will be improved if we can provide higher resolution by this approach. Because the image is not clear, but this is the result of smaller calculation based on smaller particles. So we can assume the motion near the body surface is almost equivalent to the previous one. In this case, the other part is in rough resolution because you can see any significant motion, any significant change of fluid position this side. So it indicates we do not require higher resolution. This part far from the body surface. So this is for higher resolution. Naturally, it takes long computational time. The control of resolution can be applied in many times. In this case, the original one is divided into 4 smaller particles, and each small particle will be divided into 4 or smaller particles again. So the computational cost is not significantly increased from the basic resolution, but it can show very realistic flows simulation around the body surface. So it is a merit of resolution control. You can say this condition is, with this consideration, the method of particle method goes from this level to this one. This is a comparison again. So okay. It is also possible. The application for 3-dimensional case is also possible, but I'm afraid in this case I omit the surface tension effect. So the motion of the particle is not realistic at present, but it will show the resolution change. A white particle indicates the divided smaller particles. Because it is 3-dimensional case, the division of particle is now 8. It happens like this. One particle is surrounded by other particles, and it will be divided into 8 particles. If it is successful, or the surrounding particle does not sense the division of neighbor particles. After the division, the divided new particle will continue interaction among the surrounding particles. So I think this is a good progress of particle method, but unfortunately, at present, I do not have students to tackle on this project. This is we we can calculate the lift coefficient of the planing force. This is a kind of planing simulation. Planing is planing is for high-speed ship. In high-speed ship, it will get dynamic pressure on the surface. It will lift up the high-speed boat. So this the checking of this simulation can be done by the comparison of lift coefficient. This is original. This is from MPS method in the original resolution, and this is experimental result of lift coefficient. The horizontal axis is fluid number, so in this direction, the speed of planing, speed of ship is increased. So naturally, if we provide resolution control and higher spatial resolution around the body surface, the result will be close to the experimental one. This result shows only the single stage refinement, but if we provide double or triple stage or higher stages of refinement, we can expect it will lead to higher accuracy without significant increase of computer resources. At present, it has severe problem. One problem, can you imagine the remaining problem? In this simulation, I provided division of particles, so it is definement. Remaining task is in the other direction of refinement. If it is for the simulation of a ship, flow is coming and go out. So required feature is large particle should be divided into particles to get higher resolution. Some particle will be divided also divided again, but after that, when the particles are far arrived the position far from the body surface, it does not need higher resolution now. So what we need is two merge particles to one. In this this drawing, 4 particles should be merged to one larger particle again. However, it is more difficult than the division of particles, naturally, because in the division of particles, it is very easy. We can estimate the position of new smaller particles. But in the other side of the situation, you have to find the counterpart of merging. If there is one small particles, you have to find its counterpart. if we can find 4 particles, we can consider the merge of this kind of situation. But if there is 2 particles and they cannot find any other smaller particles, we will meet significant problems. Anyway, there will be a solution. So this is smallest. If it has unit mass, and this one is 4 times higher mass, the next situation will be a 5 unit mass particle and 1 unit mass particle. One possible solution is to set the specific criteria of merging and division. The small particle will wait for the opportunity of merging. This is one solution, but it requires some consideration of possible situations. It is not solved yet. So this is the situation of particle method. Then the next thing is not from particle method. It is the discussion of ship motion in the fluid dynamic simulation. For the simulation of ship motion, we have to combine equations of Navier-Stokes and equation of motion of the ship. For this purpose, the combination can be done in this manner. Fluid dynamic simulation provides total force acting on the body surface. If it is ship simulation, the required force is the fluid dynamic force and moment on the hull surface. And this is the interaction from CFD to equation of motion. And also, equation of ship motion provides time-dependent change of boundary configuration. Because surface of the ship is also a boundary of fluid simulation. The motion of the ship affects to the fluid simulation as the change of boundary geometry, and also the change of speed of the boundary. And sometimes we have to consider the acceleration of boundary surface. And also in free surface simulation, the motion of the ship leads to the excitation of free surface. The moving ship will generate waves. And if the motion of the ship is time-dependent, unsteady motion, the free surface deformation is also unstable. With the word unstable, I remember one one thing I have to point out in the particle method. One important feature of the particle method is it does not have steady condition. In mesh-based simulation, if ship is not unsteady condition, we can get steady flow result. Although if it is mesh-based one, the mesh point on the definition point, we have velocity vectors. And if we, after the sufficient simulation time, this fluid velocity vector will be stable, constant, because this condition is a steady result. But if it is by particle method, even if you spend long time of simulation, all particles are still moving. There is no steady condition. So this is another problem of particle method. In particle method, it does not have steady condition of particles. Particles are always going. But if you are interested in unsteady flow phenomena or very nonlinear flow phenomena or wave breaking or wave turning, this situation doesn't matter. In such a case, the flexibility of particle method is a good advantage for the solution. Okay, this is an important point, but sometimes the researchers on particle method forget to say it. Then go back to the topic again. So if it is unsteady motion, the free surface is also unsteady. We have to consider the interaction between the motion of the body and fluid simulation. How to get the fluid dynamic force from the simulation is written like this. We have to consider the lateral force and moment. We have to consider both components. If it is in three-dimensional arbitrary motion, if this force, fluid dynamic force F, has three components, and also moment have three components. So it has 6 components in total, so we can solve general 6 freedom of motion, 6 degrees of freedom in motion. The force on the Hall surface is calculated by the integration of the fluid dynamic stress on the surface. This S indicates the entire body surface, wetted surface of the hull. If we wrote the contents of tensor T, it will be like this. It is viscous term. It is the viscous flux, diffusive viscous flux on the hull surface. This is new kinematic viscosity of the flow simulation. If it is high Reynolds number simulation, the turbulence model, turbulence viscosity will be inside this factor. And it has pressure part. It is the pressure. It is the force of pushing pressure on the hull surface. So if you have control volume on the hull surface, we have to consider the exchange of momentum on this interface, on this surface. In Navier-Stokes equation, there is another term, convection term. But we do not require convection term on this consideration because there is no exchange of mass crossing this body surface. So we can consider only the diffusion term and pressure term. And diffusion term is the viscosity effect. So if velocity is like this, and if it is no slip condition, the dummy point will have this kind of velocity vector. So you will calculate the velocity gradient on this surface, and momentum flux will flow into the hull surface. And in this calculation, the total integration of viscous effect is the flux it will going into the body surface. It is equivalent to the force the body will receive from the surrounding fluid. And pressure force is proportional to pressure value, and it is normal to hull surface. So on the body surface, two phenomena exist, and so for this purpose, you have to consider the conservation of momentum again. It is the end boundary of control volume consideration. So we have to be careful about this treatment. It means the momentum from this control volume to the body surface should be equal to the force the body will receive from the fluid. If these two are not consistent, it will lead to the violation of momentum conservation. It will lead to unnatural motion of the body in the simulation. The moment of the fluid dynamic force is calculated by this one. To calculate the contribution of small surface, we have to consider the center of gravity position and the present calculation point. So for this purpose, you have to know the center of gravity position. It is xz or xcg in this case. And if the body surface is partitioned by the surface mesh, the actual integration will be interpreted as the summation of summation on these panels. On each panel's pressure force is acting on, and viscous force is acting on parallel to the surface. I cannot draw it correctly. Please imagine the situation. Viscous force is parallel to the body surface, and pressure force is normal to the body surface. Anyway, this mesh surface will receive total force. And if we integrate this force all over the surface mesh, it will be the total force acting on the body. And if we consider the lever vector is a relative position vector from center of gravity to the present position. If this is F, X, the lever vector times force vector on the surface leads to the moment contribution from this patch surface to the difference point of center of gravity. So usually we will calculate we will calculate the integration of force and the moment in a single routine, because most of the calculation is the same. The important point in this consideration is this one. It will provide evaluation of viscous and pressure parts separately. It is very important. In experiments, we cannot get these two effects separately. They are mixed. But in the numerical simulation, we can get pressure distribution and its contribution, and also viscous contribution separately. It is a very good information to understand the fluid situation. Also, it will provide local contribution. if it is in towing tank experiment or wind tunnel experiment, what we will get is only the total force and the total moment. But in the numerical simulation, you can get local information. If contribution to the drag is higher in this point, you can consider the modification of these local features. But it is not. This information is not attainable in the experiments. So getting information of distribution is very important for the. It is a very important feature of numerical approaches. For the simulation of arbitrary ship motion, we have to consider moving coordinates. This is fixed coordinates. We will say ground. In aeronautics, they will call it ground fixed coordinates. But in ship hydrodynamics, they will not consider ground. So sometimes they will use earth fixed coordinates. So for the correct meaning, I have to say earth fixed coordinates. And we have to consider moving coordinates. For simplicity, the origin of moving coordinates is now on the center of gravity of the moving object. In this case, it is the center of gravity of the ship. There are two approaches for the treatment of moving ship. One is to consider only the lateral translation, lateral motion of the ship, and the calculation is also on the Cartesian coordinates. But sometimes it will make the simulation complicated. So the other approach is to consider the rotation of moving object. In this case, x0, y0, z0 is not rotating. Rotating one is x, y, z in this case. This transformation of rotation is common. It is one example of treatment of three-dimensional simulation. This is our simulation. The inflow, the entire outer domain is in Earth fixed coordinates, and the ship is in the smaller domain, and it is the fluid dynamics inside of this domain will be calculated on the moving coordinates. If we have to consider the moving coordinates, we have to consider other inertial effect. This is Navier-Stokes equation. It is written in finite volume method conservation form of Navier-Stokes equation. It is this part is the time derivative of fluid velocity, and this is the tensor of fluid stress. It contains convection term, diffusion term, and pressure term. This one is added term for the consideration of moving coordinates. This is a body force. And it has the form of, it will have this form. It is centrifugal force and Coriolis force. And this treatment, you can find this treatment in the textbook of aeronautics. It is dynamics of flight, or I don't know how to say it in English or Korean, but it is a basic equation of the dynamics of flight. Although our target is not an airplane, sometimes we have to consider the same equation, because the ship, in general, ship is moving in 6 degrees of freedom. If it is tanker model, the pitching is not significant. But if it is container ship, we have to consider pitching motion, pitching, heaving, rolling, yawing. We have to consider all the degrees of freedom. So this part should be added into the Navier-Stokes equation as the body surface effect. And after getting the information, this one is lateral force. So in the I'm sorry, it was this is lateral force, and this one is moment. So it was M, capital M vector in the previous slide. After getting this integrated information, we have to integrate the equation of motion of the ship. In this case, vector V is the velocity of the center of gravity of the ship, and omega is the angular velocity of the ship. In general, there is a center of gravity on the ship, and it has usually it has advancing motion, and it will be the vector V. And omega is the it's the rotating motion, angular velocity motion. So if it has rolling motion, the rolling axis is in this direction, and the pitching axis is in this direction. The pitching axis is normal to this board. And if it has yawing, the component is in this direction. So it has if it has pitching motion, the omega vector is normal to this whiteboard. Anyway, we have to consider this one, and H is the angular momentum of the hull. So if it is in one-dimensional rotation, H is equal to omega times I. But in arbitrary motion, in arbitrary motion, I is not a scalar. I is in tensor form. It will be discussed in the next class. Okay. Okay. Time is. Okay. Thank you very much.